I recently heard Sam Altman from OpenAI say that artificial intelligence is soon going to solve all of physics. Yeah, I don't think so. Actually, things haven't been going all that well recently with AI, and I have a brief summary for you.
The main thing that I feel is important about this technology is that we are on an exponential curve, and a relatively steep one.
That was Sam Altman last year. In an essay from September titled The Intelligence Age, he wrote confidently that AI is going to get better with scale, and it's possible that we'll have superintelligence in a few thousand days. It may take longer, but I'm confident we'll get there. A few weeks ago, he concluded that soon enough, physicists will all be superfluous.
Eventually we'll solve every problem in physics.
He's not the only one of the tech bros who's after physicists. Remember this guy Mark Andreessen, who a few months ago wrote the Techno-Optimist Manifesto, according to which, quote, "the water is warm," end quote? He has thoughts about physics too.
If you keep feeding these things enough data and enough processing cycles, they'll eventually evolve an entire internal world model, right? And they'll have like a complete understanding of physics.
This faith in the increase of AI capability is widespread. Here we have Dario Amodei, CEO of Anthropic.
From a fundamental perspective, I think it's very unlikely that the scaling laws will just stop.
And then we have, of course, Leopold Aschenbrenner, who thinks that AI will reach superhuman intelligence by 2027 or so. Reality is different. A week ago, some OpenAI employees leaked insider information to an outlet called The Information. OpenAI is currently training a new model called Orion, and while that's still in the training, according to The Information, some researchers at the company believe Orion isn't reliably better than its predecessor in handling certain tasks. Orion performs better at language tasks, but may not outperform previous models at tasks such as coding. Reuters reported that OpenAI isn't the only one running into this problem. Ilya Sutskever told Reuters recently that results from scaling up pre-training, the phase of training an AI model that uses a vast amount of unlabeled data to understand language patterns and structures, have plateaued. Bloomberg reports that Google is facing the same issue. An upcoming iteration of its Gemini software is not living up to internal expectations, according to three people with knowledge of the matter. And on X Twitter, further rumors are making rounds. Heard a leak from one of the Frontier labs. They reached an unexpected huge wall of diminishing returns. Sam Altman insists there is no wall. The reason for Altman's optimism is likely that there are several optimizations left to be done on the current large language models, which is what Aschenbrenner calls unhobbling. For example, just having these models iterate answers and thinking about them as the newest GPT does has been a huge improvement. Then again, if they don't scale with more data, this will only delay the problem. The only person who seems to be genuinely happy about this is Gary Marcus, who has predicted that this would come years ago. John LeCun from Meta and Bill Gates have also speculated about this. I can't say I'm happy, but I'm unsurprised. I'm also genuinely puzzled why these AI people think this will work. Part of the reason is quite plausibly that they need investors to believe it, but I've come to think it's partly because they don't understand physics. Listen to this interview with Ilya Sutskever, that's one of the guys who left OpenAI last year and then founded his own AI company.
Predicting the next token well means that you understand the underlying reality that led to the creation of that token. It's not statistics, like it is statistics, but what is statistics? In order to understand those statistics, to compress them, you need to understand what is it about the world that creates those statistics.
I find this very interesting because it's easy to see what's going wrong there. He seems to think that you can deduce the laws of an underlying reality from a higher emergent level. In the case of AI, you want to reproduce a physical model of the world, that's the underlying reality, from an emergent level, that's words and maybe videos, but in any case data that humans have produced. But we know that this generally doesn't work. You can in general not deduce the laws underlying an emergent level. Think about this for a moment. If this was so, why didn't Aristotle just deduce the standard model of particle physics sitting in a comfy chair staring at his hands? Why did we have to go and build huge particle colliders to get it done? It's because deduction only gets you so far. Then you'll need better data. In physics, it's called the decoupling of scales. I'd expect there to be a similar decoupling of scales between the details of our reality and our description of reality. Even if you take videos or images, these are extremely limited representations of the real world. To break this impasse, you need real-world data to train AI, and there isn't remotely enough. I've now had quite a few AI people telling me that data is not a problem, so they think I'm wrong and I think they're wrong, and I guess we'll see how it goes. But to me, training large language models with more data seems like going to the gym. At some point, adding more weights doesn't make you stronger. It just makes you more likely to drop something heavy on your foot. The Kessler syndrome is a chain reaction of collisions among space debris that, once it sets in, might leave orbits entirely unusable. In the past years, we've seen an increasing number of satellites breaking up and near collisions with space debris. So how close are we to the Kessler syndrome? The Kessler syndrome was conjectured in 1978 by NASA scientist Donald Kessler. Astronomers and space enthusiasts likewise have feared it ever since. Kessler said that once there is too much stuff circling in low Earth orbit, some of it will inevitably fall apart and create debris that'll uncontrollably splatter into unknown orbits. This can create a cascade in which debris gets increasingly smaller and eventually distributes around the entire globe. The issue is becoming increasingly pressing. In June, a defunct Russian satellite broke up into more than 100 pieces and forced the International Space Station to adjust course. In August, a Chinese rocket broke up upon launch, leaving behind more than 250 pieces of debris in orbit. And just 2 weeks ago, an Intelsat satellite suddenly and inexplicably lost power and seems to have broken up into at least 20 pieces, which is also a pretty good description of me on a Friday afternoon. And that's just what happened in the past couple of months. The European Space Agency estimates there are more than 100 million pieces of debris in low Earth orbit already, while most of them, about 130 million, are smaller than 1 centimeter in diameter. About 1 million is between 1 and 10 centimeters, and about 40,000 of them are larger than that. The total is more than 13,000 metric tons, about twice the weight of the Eiffel Tower. If the Kessler syndrome becomes reality, it might mean that we simply can't put any more satellites into these orbits. Most of the debris will fall down to Earth eventually, but leaving aside that this isn't great either, it'd take hundreds or even thousands of years. So just how close are we? In a paper that just appeared, scientists used a stochastic model for launches, re-entry and collisions and projected it into the future. For this, they assumed that the current launch rate of about 1,500 satellites per year remains stable. They find that runaway debris growth would begin around the year 2050. The projection sensitively depends on 2 factors. One is the number of pieces of debris that is created per collision, which they estimate to be between several hundred and around 1,000. The second one is the deorbit time. That's the period for how long decommissioned satellites can remain in orbit before they have to be removed, usually by burning them in the upper atmosphere. The deorbit time is currently 25 years. Reducing it to 5 years would much delay the problem and give us more time to find a way to deal with it. So how do we deal with it? Scientists and engineers have proposed various ways to deal with debris. This includes, most importantly, sweeping orbits to collect junk and then usually dumping it into the atmosphere to burn, or using lasers to nudge pieces of junk into other orbits, either to avoid collisions or, again, to force a re-entry into the atmosphere. NASA recently looked into what's the best method in in terms of cost and effectiveness, and ground-based lasers came out well ahead. You may wonder why it's better to use ground-based lasers than having them in space. This is because it's easier to generate the necessary power if you're hooked onto the electric grid. By the way, I have a free weekly newsletter with some extra content. All you need to do is sign up at sabinehossenfelder.com/newsletter. Some of these efforts are already underway. For example, the project Remove Debris, which ran from 2018 to 2019. It tested technologies like nets and harpoons for capturing space junk. These tests were successful. The harpoon hit a target and the net captured a piece. However, these were not real pieces of debris, but objects that were previously deliberately placed there. One prominent project that's currently being planned is Clear Space 1, backed by the European Space Agency. If successful, it'll be the first ever mission to actually remove debris. The plan is to use robotic arms to grab and deorbit a 100-kilogram payload adapter that's been floating around in orbit since 2013. The ESA mission is scheduled for launch in 2026. And the Japanese startup X-Fusion is quite literally aiming at the sky. In cooperation with the Australian defence company Electro-Optic Systems, they are about to use a big laser to shoot small pieces of space debris out of orbit. X-Fusion, as the name suggests, actually developed their lasers to shoot at fuel pellets of hydrogen in the hope that they'll undergo nuclear fusion and create energy. However, the laser power needed to knock a small piece of junk out of the sky turns out to be lower than that needed for nuclear fusion. So if it doesn't work out with my life, I'll just call myself X-Sabine and start shooting things out of the sky. More seriously, there's a lot of commercial interest behind keeping low Earth orbits usable, so I'm quite optimistic that something will be done about it. Or maybe our children will make a hobby of collecting satellite parts. Earlier this year, I accidentally waded into a controversy that I didn't even know was one. It happened when I made a video supporting Mark Zuckerberg's statement to Congress that there are no studies showing that social media use causes mental distress in children. This became one of the most disliked videos I've ever made. So, of course, I thought we should talk about it again. You can see in the comments of the earlier video that a lot of people disagreed, citing their own negative experience with social media. I'd never question anyone's personal experience, and trust me, I know what they're talking about. My Instagram feed once suggested salad recipes, and I'm still traumatized. But the plausible hypotheses are the ones that we need to be most careful with. It's plausible that social media is stressful and impacts mental health, and it's plausible that children are more susceptible to it. I have 2 teenagers and they're not using social media. But is this cause of distress any worse than other problems that children have always encountered? I mean, whatever happened to algebra? The idea that social media causes children mental health distress has been promoted most vocally by the American psychologist Jonathan Haidt. He recently wrote a book about it called The Anxious Generation that's been on the New York Times bestseller list for most of the year. In his book, he claims, among other things, that social media companies, by designing a fire hose of addictive content that entered through kids' eyes and ears, and by displacing physical play and in-person socializing, these companies have rewired childhood and changed human development on an almost unimaginable scale. He's also very active on X Twitter, and much of the media seems to be on his side. Smartphones and social media are destroying children's mental health. Social media is driving teen mental health crisis. Algorithms are making kids desperately unhappy, and on it goes. However, many scientists have expressed strong skepticism about Haidt's claims and are warning that they are not backed up by science. In March, psychologists authors Candace Odgers wrote in Nature magazine bluntly that Haidt is a gifted storyteller, but his tale is currently one searching for evidence. She refers to multiple meta-analyses which found that if there are any correlations between children's social media use and their mental health, they are small. Several studies found that children who already have mental health problems are more likely to use social media, which confounds the analysis. Most tellingly, an analysis of data from more than 70 countries didn't find a measurable link between children's mental health and the rise of social media use. The psychologist Chris Ferguson has called it a moral panic in which data is sidelined. Aaron Brown, a lecturer in statistics, had a look at the studies that Haidt refers to. He found that the evidence not only doesn't support Haidt's claim about teen health and mental health, it undermines it because there isn't any clear trend in the data. Imagine bringing data to back up your point and it stands up in front of everyone and says, "Actually, I don't know this guy." That's what happened here. The American Psychological Association summarized the state of research last year with social media is not inherently beneficial or harmful to young people. A report from the American National Academies of Science from last year likewise concluded that a review of published literature did not support the conclusion that social media causes changes in adolescent health at the population level. This isn't my research area, but one thing seems pretty clear. The very fact that it's controversial already tells you that if there's anything, it's not much. There seem to be some small studies showing, for example, that taking several weeks of social media does improve children's well-being. And this might well be, but this is very different from claiming there's a systemic effect changing children's brains. Don't get me wrong, everyone, including myself and even Mark Zuckerberg, agrees that social media is currently dangerous for children. Most worryingly, it's because they might be exposed to content that isn't age adequate. Pornography, violence, debates about interpretations of quantum mechanics. Stuff you don't want your children to wade into unsuspectingly. Or joking aside, there have been extremely tragic cases of children who participated in viral challenges such as swallowing a spoon of cinnamon powder or strangling themselves. Some ended up with permanent injuries, some died. The Australian government now simply wants to forbid social media for children below the age of 16. And in lack of a better solution, that seems like a good idea to me. But the great rewiring of children's brains just isn't happening. The reason I'm telling you this is that I found it rather disturbing how disconnected media coverage on the matter has been from the scientific debate until recently, and I'm afraid that science is losing the social media battle. It'd be a shame because in the end, as any technology, social media is not inherently good or bad. It could be either depending on how we use it. Like you could use a hammer to build a bookshelf or use it to smash your phone after your 4 millionth notification of the day. But if you do, please make sure to record it on video and share it on social media. This video is about a story that's been going on for 2 years, which I find unbelievable. It's that the Webb telescope found evidence that clearly contradicts predictions made with dark matter, and it instead confirms the predictions made by the computing theory modified Newtonian dynamics, and no one cares. Maybe I shouldn't be surprised, because Stacey McGaugh has told me that this would happen. But I guess I didn't really believe it until I saw it with my own eyes. You see, the hypothesis of dark matter predicts that galaxies should form very slowly and gradually during the history of the universe. In the early universe, there should be only small galaxies. Then they collide and merge and grow to increasingly larger ones. It's like what happens with dirt under the sofa. You buy a new sofa, wait for a few billion years, and suddenly you have dirt balls sitting underneath it. Astrophysicists think that galaxies form just like that. Specifically, the galaxies with the typical sizes that we see around us today should be only about 6 billion years old. Until recently, that was plausible because we just didn't have any data for older galaxies. But the Webb telescope changed that. Astrophysicists quibble about the details, of course, but they agreed on this, that the early universe should not have big galaxies and that they form very gradually. This is indeed exactly what they calculate with these computer simulations for structure formation, like the one you see here. They show the gradual buildup of galaxies, mostly from the mergers of, here it comes, dark matter halos. This figure shows what's called a merger tree for the simulation of one particular galaxy. You see that it starts out from a lot of small ones and then they merge, mostly in pairs, and then they merge some more, and eventually there's only one big galaxy left. In modified Newtonian dynamics, MOND for short, galaxies form entirely differently. Just as a reminder, this theory doesn't contain dark matter, but instead says that gravity works differently than Einstein predicted. Albert doesn't like this at all, but he's really trying to be open-minded. Specifically in MOND, the gravitational force doesn't fall off as quickly as large distances or low accelerations as it does in Einsteinian gravity. This effectively increases the gravitational pull in early galaxy formation, so they form faster. This is a solid prediction from MOND that dates back to the late 1990s. The prediction from dark matter has been refined over the years, but this gradual merger story has remained the same. You can see a comparison between the two predictions in this figure. I even mentioned this prediction in my video about the Webb telescope before it collected any data. And what Webb has seen disagrees with dark matter, and it agrees with MOND. You've almost certainly seen the headlines. Webb has found big galaxies considerably earlier than what dark matter models predicted. They're too big, too early, they shouldn't exist. Astrophysicists reacted by questioning the data, and when that fails, they'll try to fumble with the dark matter models to make them fit the unwilling data, which they have already begun. That doesn't surprise me. What surprises me is that the people who write about it in the popular science press don't even mention that this was predicted by the competing theory. It's like running a review of The Empire Strikes Back and not even mentioning Darth Vader. Minor detail. Just the other day, a new paper appeared that analyzed the new Webb data in detail and that shows just how far it's away from the predictions. This figure is very telling. You see these lines of different color? These are the predictions from the dark matter models for galaxies at different brightness at different ages. The dots, that's the data. The blue dots should be on the blue line, the green dots on the green line, the orange dots on the orange line, and so on. You see that the dark matter prediction doesn't fit the data at all. Another figure from the same paper shows that modified gravity works much better. In this figure, the dots are observations for galaxies at different ages and sizes. The further to the right, the earlier in the history of the universe, and the further to the top, the bigger. The dashed red lines are the dark matter predictions. You see again that dark matter predicts that galaxies grow late, and there are no dark matter predictions that account for the old and big galaxies. The black lines are the predictions from modified gravity that account for the observed data. This is pretty damning, isn't it? This is a clear-cut case where two competing hypotheses were tested on data. One won, one lost, and no one even mentions the winner. It's like covering the US election results with Kamala lost because you're afraid to mention Trump. Are you still wondering why I'm skeptical of the idea that science self-corrects? In the past decade, astrophysicists have dramatically shifted their opinion about dark matter. The most popular idea is still that it's made of particles, but it's now a different particle called the axion that's attracting most of the attention. This graph shows the number of publications about these axion particles each year. As you can see, it's not entirely a new trend, but axion research really started taking off about 10 to 15 years ago. What happened then was that the LHC failed to find the biggest competitor of axions, the WIMPs. WIMPs are weakly interacting massive particles. They were expected to have masses comparable to the heaviest particles that we know of, like the Higgs boson. This is why they should have shown up at the Large Hadron Collider. They didn't. That doesn't mean they don't exist, though. They could just be even heavier, so we'd need a bigger collider to produce them. WIMPs were appealing candidates for dark matter. For one thing, because they came together with many ideas to unify the interactions in the standard model, but also because of the WIMP miracle. If WIMPs have masses in the LHC range and interact roughly with the strength of the weak nuclear force, they would have been produced in the early universe in roughly the right amount to fit to observations. No WIMPs have been seen anywhere, not at the Large Hadron Collider and not in any of the many experiments looking for them. But these experiments all resulted in constraints on the masses and interactions of the WIMPs. This didn't rule WIMPs out, but it removed their greatest appeal, the WIMP miracle. If you look at the number of papers, WIMPs clearly have their best time behind them. Enter axions, or rather re-enter. The axion was introduced to physics in the 1970s. It quickly turned out, though, that neutron stars could emit a lot of those axions, that it cooled the stars very quickly and was incompatible with observations. The axion was ruled out less than 2 years after its introduction. But in 1981, physicists introduced a new type of axion. It was originally called the harmless axion or invisible axion, because it was designed to be compatible with observations. Today it's often just called the axion. I guess they figured invisible axion was a bit too on the nose. Like WIMPs, the axion doesn't interact with light and just goes through normal matter. It therefore could make up dark matter. However, in contrast to WIMPs, axions have extremely small masses. This means they are basically impossible to detect in particle colliders. That's because they go through detectors. So to find out whether they were there at all, physicists just check whether energy went missing. This works for particles with high masses like WIMPs, but for those with small masses like axions, the missing energy is below measurement accuracy. It's like trying to find a needle in a haystack, except the needle is invisible and the haystack cost $5 billion. But these small masses make axions appealing candidates for dark matter. This is because the quantum uncertainty of a particle depends on its wavelength, and the smaller the mass of the particle, the larger the wavelength, so the larger the uncertainty. For very small masses, the uncertainty can extend through entire galaxies. This is neat because the distribution of WIMPs usually comes out to have a sharp peak in the centers of galaxies, which is incompatible with what we observe. Axions alleviate this issue because their large quantum uncertainty blurs out the peak. Basically the same idea as photoshopping pimples. Another reason axions have risen in popularity is that physicists stopped worrying about the reason they were unpopular in the first place. Axions don't fill the universe the same way as WIMPs. They don't form clouds of freely floating particles. This is what WIMPs do. Instead, axions form a condensate in the early universe. You could say they're more like puddles than like clouds. Physicists used to worry that to get the properties of the axion condensate to come out right so that it fits to observations, they had to fine-tune some numbers. They have more or less stopped worrying about this now because any solution is better than none. One can look for axions with direct detection experiments. These experiments use strong magnetic fields, which should convert axions into photons. Some of these experiments have been running for a long time, but haven't found anything. There have also recently been claims that axions can collect around rotating neutron stars known as pulsars. Since pulsars have strong magnetic fields, the axions would leave a characteristic signal in the radiation we receive from the pulsars. This is a great idea because it could finally help us pin down the dark matter particle. If you've already forgotten half of what I said, this video comes with a quiz that'll help you remember what we talked about. Most astrophysicists think axions next to WIMPs are the best motivated candidates for dark matter because their existence is a consequence of other ideas. In the case of WIMPs, that's the unification of forces. In the case of axions, that's the solution to the strong CP problem that keeps a standard model parameter small. I think neither of these motivations are particularly good, but then again, I might be wrong. And the axion could just be the scientific version of that spare IKEA part. You're not quite sure what it's for, but hey, it could hold the whole thing together. Today I have good news. We can finally lay to rest the idea that our universe is somehow especially hospitable for life. It just isn't. I think it's good news because this argument has sometimes been used as support for the existence of a creator, and worse, for the idea that we live in a multiverse. Let's have a look. The anthropic principle at first sight seems to simply be a tautologically true statement. We can only observe laws of nature that allow for the existence of observers. It sounds like a joke a 5-year-old might make, but naive truths can be very revealing. The anthropic principle is not entirely useless because the observation that the universe is hospitable to life gives us constraints on the laws of nature. They need to be so that we can exist. The most famous use of the anthropic principle was when the physicist Fred Hoyle predicted the properties of the nucleus of the carbon atom. His argument was that life on Earth needs a lot of carbon, but carbon wasn't produced in sufficiently high amounts in the early universe. So where does it come from? It must be produced in stars by nuclear fusion. And this can only work if the carbon nucleus has a particular property which Hoyle predicted. And he was right. In all fairness, Hoyle's argument didn't have much to do with life in particular, but just generally with the observed abundance of some chemical elements. But in the end, it doesn't matter all that much just how physicists get their ideas, so long as they work. This is why I think using the anthropic principle is all well and good. But in the past decades, it's become connected with the multiverse, and that bothers me. The multiverse is the idea that there exists not just this one universe, but a large or even infinite number with different laws of nature. This raises the question, well, if there are so many universes, why do we live in this particular one? One way to approach this problem is to ask what's the probability for life to arise in any of these universes, and how many observers inhabit each of them in the entire lifetime of the universe. We're most likely to find ourselves in a universe that hosts a large number of observers. So if we find that the laws of nature in our universe are not optimal to produce observers, then that makes it unlikely the multiverse idea is correct. Just among you and I think that's nonsense. You can't stochastically sprinkle observers over universes like chocolate on a cake. That makes zero sense. But let's leave aside my misgivings. This is how the argument goes. Instead of laws of nature, one usually looks just at the known laws of nature and changes the constants. Then you calculate the probability for life to rise and observers to exist for each set of constants. And if you find that the constants in our universe are so that it's likely to contain a lot of observers, then that supports the multiverse. There have been a bunch of arguments that indeed the constants in our laws of nature are especially fine-tuned for life. But the results of this new paper say it's just not the case. They looked at the question of what value of the cosmological constant would be best for the emergence of life. The cosmological constant, lambda, is the simplest type of dark energy, and it determines the expansion of the universe. It has a major influence on the rate of star formation, and with that it strongly determines the probability for solar systems with planets that are hospitable to life. The cosmological constant plays such an important role because for stars to form, matter needs to clump. The larger lambda, the faster space expands, and the harder it is for matter to clump, so there'll be fewer stars. On the other hand, if the cosmological constant is very small, then matter clumps too well. That leads to a lot of big, large-scale structures with dense gas, but fewer star-forming regions. This means if you want solar systems with planets that can harbor life, the cosmological constant should be neither too small nor too large. In the paper, they calculate which is the optimal value and find that it's about 400 times larger than the one that our universe actually has. Consequently, our universe is not especially inhospitable for life. As they write in the paper, the observed value of the cosmological constant appears to be unreasonably small compared to the predictions of the simplest multiverse ensemble. This poses a challenge for anthropic reasoning as a viable explanation for cosmic coincidences and the apparent fine-tuning of the universe. So can we conclude that the multiverse was falsified by evidence? Unfortunately not, because you can fix this problem by saying that the probability distribution of observers over the universes was somehow more complicated. And I'm afraid that's what theoretical physicists will do now. After 10 more years and several hundreds more papers, they'll conclude that the values of the constants of nature are what we already know they are. I can't wait. Somewhat more seriously, while there'll without doubt be some physicists who will continue working on this, I think this means that multiverse enthusiasm has peaked and will slowly decay from here on. Progress! Yay! Thanks for watching. See you tomorrow.